Hi, this is Hassan Beg. This demonstration is created on Macintosh OS, and same procedure and these steps are applicable on the Windows version as well. This is the D-VASim directory which contains sim underscore results folder. All the simulation data are stored inside this folder. Now let's start D-VASim by double-clicking on the icon. SBML model of a genetic circuit can be loaded by pressing the browse file button. Let's select the SBML model of a genetic circuit created by some other researchers. Let's select the OR-gate model. The schematic diagram of this model is shown up here, which says that whenever either of LAC-I or TETR is present inside the cell in significant amount, that is above their threshold level, they suppress the production of CI or CRO respectively. This in turn activates the production of output protein GFP. Now you can analyze the SBML components of this model in a friendly manner here. You can see the list of species used to construct this genetic circuit. You can further check the list of parameters which are used to develop this model. You may also have a look at the reaction kinetics of this model, the kinetic laws, and the ordinary differential equations. Similarly, you can see other components of the SBML models. For simulation, we have either of these two options available. First one generates a virtual instrument for stochastic simulation, and the other one generates a virtual instrument for deterministic simulation using ordinary differential equations. Now let's create a virtual instrument of this model for performing stochastic simulations. So the virtual instrument for stochastic simulation is created. D-VASim identifies the external inputs of a model and create control knobs to let the user change the input concentrations during runtime. User can also create control knobs of other species by going to the Options drop-down menu and selecting external inputs, where they can drag the name of a species from left-hand box to right-hand box which they want to control during runtime. At the time of starting simulation, as a user I may not know what is the threshold value and a propagation delay of this model. So I would change this toggle switch to auto mode and press the run button. A setting box will appear. The settings are described in the user manual, so I'm not going to explain these settings in this demonstration. Okay, so it will take some time to estimate the threshold value and propagation delay of this circuit. Meanwhile, we can have a look at some other options available in this VI. User can perform simulation for a predefined interval of time by turning this toggle switch to no and specify the time interval down here. User can also control the speed of simulation in milliseconds with the help of this control box. So now we have the estimation of the threshold value and propagation delay, which says that minimum of 15, let me assume a unit of molecules. So 15 molecules are required to trigger the output. The concentration level above this value will be considered as logic 1, and below this value will be considered as logic 0. It also shows the propagation delay value with the standard deviation. In this case, it shows the estimated propagation delay value is 364 time units plus minus 62.80. It means that when the inputs are triggered to their threshold level, it will approximately take 364 time units to reflect this change on the output. Output consistency indicates that the estimation which D-VASim has just performed behind the scene are 94.87% consistent. Now press the OK button to begin the simulation. So this is a 2-input circuit, therefore total possible input combinations will be 4. User have to apply all the input combinations in order to extract the correct Boolean logic. However, it is not necessary to apply all these combinations in a standard sequence, that is 0, 0, 0, 1, 1, 0, and 1, 1. We can apply these input combinations in any sequence. Let's apply input combination 1, 1 first by increasing the input concentration above the threshold level. Because the estimated threshold value is 15. We can see that the inputs were triggered around 900 time units, and the output is started producing after nearly 300 time units, which was the estimation of D-VASim. So at this point, if you want to perform logic verification and analysis without applying all the possible input combinations, we can click on the logic verification button, select the output species from the drop-down list, which is a TFP. The threshold values are already extracted from the previous estimation, so press OK. Now it says that an AND logic exists between inputs and the selected output. It also says that all input combinations are not applied correctly, which means that the above logic behavior may not be true for this circuit. Therefore, in order to extract the correct Boolean logic, we need to apply all possible input combinations. Now let's go back to the simulation environment and apply rest of the input combinations. We already have applied input combination 1, 1. So let me apply input combination 0, 1. And I would just like to mention that the model parameters that are extracted from the SBML model, SBML file, they can be changed here and during runtime simulation. So we can observe the effects of changing parameters, circuits parameters, all during runtime, just like we observed it in the laboratory. Now let me apply other input combination, which is 1, 0. You may also have noticed that the input concentration remains constant, which is not the case in the real-world experimentation. The user can mark this option check to let the input concentrations degrade over time to perform more realistic simulations. Now we are left with only one combination, which is 0, 0. Let me apply it and give it some time to reflect this change on the output species. Speed the concentration. Alright, now we can execute logic verification again. Output species already selected. So it says that model has a behavior of OR gate with inputs like I and TETR. It also shows that above expression fits 99.48% in the entire simulation data. We have all the simulation data here with the analog and digital. User can also analyze the digital waveform of this model to perform timing analysis more conveniently by going into the Options drop-down menu and select Mixed Signal Waveforms. So here user can analyze the model's timing behavior more easily. You can see that there are some glitches when both of the inputs are triggered to 1, and even we can notice that when we trigger inputs to 1, the output is triggered after a certain amount of time, which is the propagation delay. So we can also capture the graph, and we can see the files that we have generated here, which is mixed signal waveform graph, and this is the whole simulation data. Now we can close it and stop the simulation. If user wants to perform logic analysis on intermediate circuit components, they can change the input list from the drop-down menu, external inputs, Let's remove the ETR and keep black eye only, and turn this to manual mode because we already know the threshold value, and run it again. Now we can see what is the logic relation of black eye with any other species of this model. Let me first trigger black eye to its logic 1. Since there is only one input, so we have only two possible input combinations, that is 0 and 1. So 0 has been applied in this time interval, and now this is 1. We have already applied. Now let's trigger the logic verification option again and find out the relation between LACI and say CRO. Press OK. So it says there is no logic access between LACI and CRO. We can see that in here as well. LACI and CRO have no direct relation. Now we can close it and run the logic verification again and select CI now. And there we go. It shows that an inverse relation exists between these species, which is true according to the circuit schematic. So this is it. This was a very short demo of D-VASim. We believe that D-VASim can help students, biologists, or genetic circuit design engineers to analyze and simulate the circuit's behavior and obtain the correct set of parameters prior to creating them in the laboratory. This is analogous to the design flow of electronic circuits, where circuits' behaviors and timings are first simulated before fabricating them onto a silicon wafer. So thank you for listening and watching this video demonstration.